merge sort. So what we will do, if we have array, so I will be explaining it with the example of array. Say I have an array of n elements, so in this case I will take finite array of 7 elements. Say I have array named 50, 80, 20, 16, 13, 55 and 35. So these are, I will start indexing from 1, 2, 3, 4, 5, 6, 7 elements, right? Basically in C programming, array starts from 0, right? So how we will be sorting? I will make it as a problem. We are taking input an array of n elements, and what we need as output, we need output of a sorted array, right? And we will be sorting it with the help of merge sort, right? So first of all, in algorithm procedure, we need to identify when the problem is small, right? Small, I mean to say when we don't need to apply any algorithm, so that we consider as a small, right? So means when we don't need to apply a recursion on the algorithm, so when we call it a small. When we have, if we are having one element only, then we don't need to apply any algorithm on it or any recursive procedure on it, because one element is already in a sorted order, right? So if we are having more than one element, then we will try to apply a procedure that is called merge sort, right? So I will define a key element here, or keyword here, mid. Mid will be I plus j divided by 2. So in system, if I take, in programming, if I take integer, that will take floor value. In mathematics we write it as floor. So I here is 1 plus 7 divided by 2. So in this case, mid will come as 4. So what we are trying to do? So I will dry run the algorithm first. So we have an array. It is having starting element as 1, ending element as 7. Now I have divided it till mid. So in this case, mid is till 4. So I will take this left part is from 1 to 4, and right part will be having elements 5th and 6th, right? The left out elements I have written, right? Means this is called mid only, right? From 1 to 4 and then 4 to 7, right? Taken it till mid, so it is from 1 to 7, and then from 5 to 1 to 4, and then from 5 to 7, right? Again I will divide it into mid procedure, right? So 1 plus 4 divided by 2 is 2.5, right? So that will be, A will go from 1 to 2, this part, right? And then after 2, right, 3 to 4. In left side also, if I take mid, right, 7 plus 5, 12 by 2, 6. So 5 to 6, and this is A 7 till 7. So we have to stop till one element to mid. So this is how we will get the tree. So after 7 7, it will be like 1 plus 2 divided by 3, then it is 1.5, and so we will reach till single elements, right? And we will keep on dividing when our problem is small, right? So we'll see how this is being called in the stack. So this is our first call, right? Then after mid, this is second call, then this is third call, and this is fourth call, this is fifth call, right? So when left is finished, then we'll go to right, right? Then it is sixth call, seventh call, eighth call, right? And then we'll go to the right subtree, 9th, 10th, 11th, 12th, and this is 13th call, right? So this is how it is being evaluated in the tree, right? So this is just a call. I will just write, actually every data structure is being implemented in stack, right, for the processing of data. Means mostly linked list are available on heap also. So in this case we are making it in the stack, right? So how it happens is, this is how it is being called, and we will see how it is being evaluated. So first of all, the things which will get evaluated will be, we will move, after this thing we will move to the left side, because all of these are dependent on each other. Then we will move further in left side. So first of all, this thing will get evaluated, C4, then C5 will get evaluated, and when both of these are evaluated, then C3 will get evaluated. So I will just write how these things are evaluated, right? So value how we will get. So first C4 will get evaluated, then C5 will get evaluated, then in turn it will give us C3 as an output, right? Then C7 will get evaluated, C8 will get evaluated, then in turn we will get as C6, right? After that, when C3 and C6 are available, right, then C2 will get evaluated, right? Similarly on the right side, we will go, C9 is dependent on C10, C10 is dependent on C11. C11 will get evaluated, then C12 will get evaluated, after that C10 will get evaluated, and C13 is already, means it does not need any further processing. So C13 and 10 are evaluated, then C9 is evaluated. So this is how this tree is being evaluated, right? So execution order is, every child is being processed first, right? Every child of this tree is being processed first, right? So this is called post order. This is called post order, means root is being evaluated after the children, left child, right child, and then root. This procedure is called post order traversal, right? So merge sort is being evaluated in post order, evaluated in the stack. Actually, how this is being stored in the stack. So there is very short funda. You invert this tree and fit into the stack. This is how it is being evaluated at first, right? Now I will show. See, this is the stack memory. Say first call will go at the bottom of the stack, right? Then after that, second call will go up on the stack, then this is third call will go, right? And now you see C4 will come. So as soon as C4 is coming, so this problem is small, there is only one element, so this will get executed and it will go out of the stack, right? So I will just cross mark it, because it has been evaluated, right? So as soon as C4 got evaluated, then after that C5 will go inside the stack. So when C5 call 5 has been evaluated, it also, because it is also having only one element, this also will get evaluated as soon as it entered in the stack, because one element is already sorted, right? Then C6 will not get evaluated, then because then C6 should come into the stack, right? After C5 get evaluated, so both the childs are being evaluated. Then after that, what will happen? It will remove C3 also out of the stack. So just to make it C3 means both child has been evaluated, then root also got evaluated, right? So now if C3 is out, now C2 is looking for its children's to get evaluated first. Then C6 will go inside the stack here, and C6 is dependent on C7. So as soon as C7 get inside the stack, this get evaluated as soon as it enters in the stack. Then C8 will come inside the stack, right? And that C8 also will get evaluated as soon as it comes into the stack. So when C8 also is evaluated, then C6, because these are children of this only, right? C6 only. So C6 also pops out of the stack, right? Now when C6 has been popped out, so in left subtree C2 also will get popped out, because till this point left subtree has been evaluated, right? That's how that log n is coming. We will see later, right? Now C1 to get evaluated completely, it needs right subtree also. So after it gets C9 as input. C9 require C10, right? To get evaluated, C10 require C11, and C11, as since it is having only one element, we are talking about this, right? So this get evaluated, and then it gets C12 into the stack, and C12 also, as soon as it reached, it will get evaluated. So since C11 and 12 got evaluated, C10 will pop out. C10 got evaluated. Then after that, C9 to get processed, it required C13 also. So then C13 will go into the stack, right? So since this part is empty, so here C13 will go inside the stack, right? And as soon as C13 come, it is one element only, this get evaluated. So now C13 and C10 both are evaluated, so C9 will get. So when I am crossing, that means it is popping out, right? That means it is popping out of the stack. So C9, so C2 and C9, then C1 will get evaluated. Now the way I have written this stack, right, this is how it happens in stack, and stack itself, one stack itself is sufficient to get this evaluation, right? So this is how it goes inside stack. Now if you watch it closely, right, you just invert this tree and that is your stack actually. So that's why trees are very important to understand the data structures, right? You see C4, C5, C7, C8, C11, C12. C4, C5, C7, C8, C11, C12, right? All the leaf nodes are on the top of the stack. This is actually an interview question also. So on the all the same level nodes will remain on the same level in the stack. Means if I level this tree as 1, 2, 3 and 4th level, so this will be 4, 3, 2, 1. So 4th level is having all the nodes which are on the 4th. So 4th level of the stack is evaluating all the values which are on the 4th position, right? So this is how it is being evaluated in the stack. How this tree is being evaluated in the stack, right? So we have seen all the leaf nodes, right, are going in the same level in the stack, right? And in fact, we have seen that first one half of the tree is being evaluated, right? Right, and then second half of the tree is coming inside the stack and is being evaluated, right? So that's how the stack space, right? So stack space, right, that comes into space complexity of the algorithm will come as log to the base 2n, right? Means it is order of, right? We all know what is the meaning of order of, right? So see, now you see there are total number of how many elements, right? If means in tree, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So means if you write it like log to the base 2 raised to power around 4, right? 2 to the 4 to the 8 to the 16, right? Around 16 element, right? So this will give you 4 levels, right? 4 levels of the tree, and these 4 levels is taking memory in the stack, right? So these 4 levels only has been used in the stack, means stack space is used as 4 chunks of memory only, right? So that's how stack space complexity comes at order of log n, right? Order means it is smaller than this value only, it will not go beyond that, right? So this is how stack space complexity will come, right? Now if we see in here in this tree only, so now I will rub out the elements. I will see, if we see this tree only, and we will see how this element is being evaluated. So we will understand that with the help of this tree only, how these elements are being stored here, right? Because now we have seen the procedure also. So I will take some other pen and we will focus on this tree and how these things is being evaluated. Now we go take 50, right? So 50 will reach till here, right? This is 50, right? First element, right? Second element is 30, third element is 20, second element is 80, okay? it is 80, third element is 20, right, and fourth element is 16, right, 16, right, I will just write over it 16, and then it is 13, this element is 13, this is 55, and this is 35. This is how the elements are being, means it will divide and reach till single element. Now while sorting, right, so how it is being evaluated? First both the child is being evaluated, means we will compare these two elements, right, and we'll get 50 to 80, right, we will sort this out, right, we will divide, sort this out and store back in C3. 20 and 16, it will come as 1620. 13 and 55, it will come as 1355, and this is already sorted. Now these two elements, you see what I am trying to explain you, while merging, right, while merging we are having two sorted subarrays actually, right, this is also being asked in the interviews, right. So now how we will compare 50, 80, 16, 20. So usually these are sorted, right. So usually we compare this with first element and we'll get which is the smaller. So 16 is smaller, right, and then 50 and 20. So I will tell that algorithm also, we will just write it first, 16, 20, 50, 80, and from this side we'll get 13, 35 and 55, and now these two are sorted two subarrays, right. So now if we sort it, it will come as 13, 16, 20, 35, right, and then 50, 55 and 80, right. So while merging, so this procedure when we are moving back, right, when we are moving back and combining, this procedure is called merge procedure, and we will see the algo to merge it. So first we took an array, we divide it into subpart, we reach till one element, then we have seen how it gets stored into stack and how we will get the space complexity of the stack. Now I have shown you how to merge them back, right. Now we will see how to write an algorithm to merge those elements, right. So with two subarrays, right, I will take two bigger subarrays, right, and show you how to merge. So that is called merge algorithm, right, and this merge algorithm is only being called in merge sort algorithm, right. Fine. An example how this merge thing is being happening, right. I told you, right, from here 50, 80, 16, 20, and this will come as 16, 20, 50, 80. So how this thing is being evaluated? So I have taken bit bigger array so that we can understand it properly. So what happens is, this is having 8 elements, so after mid, right, because this is how elements will get divided, right. So after mid we will be having two sorted subarrays, right. So what I will do, I will just show you how it is being compared. So first element, right, this 10 is being compared with 11. So I will just write this 10 is being compared with 11, which is smaller, 10 is smaller, right. So I will be having equal size array, which will keep minimum value here, right, and this pointer will move further now, 20. The value which has been stored, that pointer will move further, right. So now 20 will get compared with 11. Now 11 is smaller, so this 11 will get stored. Now 11, so this pointer will move further, right. Now the value which is smaller has been stored. Now we will be comparing 20 with 21, right. So 20, 21, 20 is smaller, so we'll store 20 here, right. So now this pointer will move further, right. So now 30 is being compared with 21. Now 21 is smaller, so this pointer will move further, this value will get copied and this pointer will move further. So now we have 31 and 30, right, 30 and 31. So which is smaller? 30 is smaller, 30 is being stored, right, so pointer is being moved further, right. And now we have to compare 40 with 31. So 31 is smaller, right, so 31 is getting stored, right. right? And this pointer is moving further till this. Now this sub array is finished, right? So what we have to do after that, just copy the remaining array, whichever array is remaining, just copy that, because it is already sorted, right? So this 30, so this value is remaining, that is 40, right? Okay, so these are having equal elements, so it will move to 40 and this will get evaluated as 40 to 41. So 40 is being evaluated, and then store this value as it is. Now this comparison has been finished because it is having equal number of elements, right? 1 2 3 4, 1 2 3 4. So every time you are comparing each value, right, with one and another, and you're storing. So when we are using the separate subarray, right, that is called outplace sorting, right? We are using separate array to store sorted value. That is called outplace technique. Outplace sorting. This is called outplace sorting. Now I will get very interesting example to explain you further. The thing which I was saying, if one subarray is finished, so second subarray will get stored. So we'll take one more example. Say you are having these two subarrays, right? So I will write an example: 40, 50, and then 10, and 70, 80, right? So it will not be 10, it is 60. 40, 50, 60, 70, 80, then it is 90, and this subpart is 10, 20, 30, right? This case also may arise the way we have seen in here, right? So one subarray can be bigger and other subarray can be smaller. So how this thing is being evaluated, that we'll see. So we'll apply the same procedure. I have two pointers. You can get this, the reference of this in Coreman also. This is how they have done also. So first 40 and 10 is being compared. 10 is smaller, 10 will get stored, the pointer move further. Then 40 and 20 is being compared. 20 is smaller, 20 will get stored, right? Pointer will move further. 30, 40 and 30 is compared, and 30 is smaller, right? Now this array has been finished, right side array has been finished, right? So now 40, right, left side array will move as it is on the right side, right? Why? Because there are no elements to compare itself, right? So first we have sorted, then we will take left side and we'll put it as it is. It will automatically get sorted, right? So this was what I was referring to, right? So now there is one more very important thing, that is number of comparisons, right? So if we have m elements in left subarray, n elements in right subarray, right? So number of comparison exactly will be m plus n minus 1, right? So last element we need not compare, the way we have done here, right? 40 is stored, right? M plus n minus 1, right? So usually we divide it into n by 2, right? N by 2 size. If means this is the general notation, m and n, right? But if we have n size subarrays, means this is how it is being written in books also. So it will be, we are dividing it to n by 2 one subarray, n by 2 second subarray, minus 1. So that will be almost equal to order of n. So your merging algorithm will take order of n time complexity. That this is very important actually, right? So comparison time will be order of n, number of comparison time, right? You got my point, right? So number of comparison is order of n, we write it like, right? So usually how we write the time complexity, it is number of comparison प्लस नंबर ऑफ मूव्स, कि कितना टाइम लगा यहाँ से यहाँ मूव करने के लिए, कितना कंपैरिजन लगा. तो नंबर ऑफ कंपैरिजन कितने हैं वैसे, m प्लस n, राइट राइट. नंबर ऑफ कंपैरिजन कितने हैं, m प्लस n, राइट. एंड नंबर ऑफ मूव्स, नाउ द थिंग कम्स एज नंबर ऑफ कंपैरिजन कैन कम लेस आल्सो, राइट. m और n है, ठीक है. this can come less also, but anyway you have to move all these elements, right, to lower order, right? So in this case moves will always be higher than comparison. Means comparison can be exactly till number of moves, right? But it cannot go beyond number of moves. Why I am focusing on number of moves? Because anyway you have to copy this whole array to next outplaced array only, right? So number of moves will be always be higher. That's how it takes overall time complexity as order of n. This is comparison time. Comparison time complexity is m plus n minus 1, that can be written as n by 2 minus 1. So total time complexity is number of comparison plus number of moves. Number of moves will always be higher because we have to move complete array into second part of array. That's how time complexity of merge algorithm, not merge sort. Merge algorithm is order of n. To write algorithm for it, right? So since we are comparing two elements, so I will just write this as I, right? And this as j, right? So merging algorithm we are writing first. Merge sort we will see later. So I will just name it as merge, right? This is first I will take starting of the array, right? Left part. So first I will take complete array, right? A complete array instance, right? And then I will take starting of the array. So I will just write A. Then I will take starting of the array I. Middle part of the array I will represent it as mid. K last part, and J is this point, right? This point is J, right? Fine. So in fact I will represent K, I will write K is equal to mid plus 1. Okay. So now I am representing this as K, representing this thing as K, this is J, right? So mid plus 1 is K, right? So just write a algorithm while I is less than mid, because I have to traverse left side of the subarray. I is less than mid and K is less than J, right? Less than or equal to J, right? Less than or equal to mid. What I have to do? If it's very easy actually. If A of I, the element, if this element is greater than A of K, right? So what I have to do? This array I am representing with B. Every index of this array I am representing with M, right? New subarray that is named as B. So what I will do? B of M. So M index is 0, right? B of M will be equal to smaller element AK, right? And then when smaller has come, right, what we need to do? Move M plus plus, means B, यहाँ M was 0, right? तो यहाँ से M plus plus आगे चले जाओ, right? And also move the smaller element was K, right? So then move K plus plus, right? And if this is not the case, then होगा क्या? If this thing is not the case, then होगा क्या? J जो है I is smaller than K, right? Then what we need to do? B of M is equal to A of I. मतलब I वाली वैल्यू छोटी है, राइट? और अब क्या है? M प्लस प्लस एनीवे M we need to increase, right? And in this case move I plus plus, the way we have understood, right? So this is else part, right? So this comes under else part, right? And this sums up your algorithm itself, right? And this is complete while loop, you have to do it, right? And in here, right, in here till merge, because if one of them is finished, so I am just writing remaining element copy, means if one of the subarray is finished, just copy remaining element in B of M, right? That is like very easy to write. So this is how we write merge algorithm, right? Here K is mid plus 1, right? You can declare it here, K is mid plus 1. So this is how we write merge algorithm. The same